Look at these digital letters snapping into solid, unyielding metallic blocks. As humans, we read text as a fluid, continuous stream of meaning. A machine, however, strips away that illusion, locking data into a rigid physical architecture. In Python, a string is strictly defined. It is not a word, a sentence, or a paragraph. It is an ordered sequence of characters, where each individual symbol is mapped directly to a specific coordinate in system memory. We establish this structure through a standard variable assignment. By writing name equals computer, we instruct the computer system to allocate memory for that exact sequence of 8 characters. Because it looks like everyday text, a common misconception is that this object is fluid. They assume they can easily reach into the word and swap out a single letter, the same way they might use a backspace key in a word processor. Python rejects that assumption. Strings in Python are immutable objects. This immutability rule dictates exactly how we must architect our data operations moving forward. If we violate this rule by isolating the first letter and changing it in place, writing name 0 equals k, we trigger an immediate system failure. This code editor screen captures the result, a type error explicitly stating that a string object does not support item assignment. The compiler refuses to execute the mutation, halting the script. This error reveals how Python handles memory allocation. Once a string sequence is forged in memory, the underlying characters are physically locked. They cannot be overwritten, edited, or deleted in place. To change text, you must systematically generate an entirely new string object. If you want the word computer, you have to allocate fresh memory for a new sequence and abandon the old one. Since we cannot alter data in place, we have to master the rules of spatial addressing. We must learn how to navigate the sequence grid to extract, compute, and spawn new data. The word Python is broken into 6 memory units. To locate characters, Python uses a dual coordinate system. Reading left to right, positive indexing starts at 0 up to 5. Reading right to left, negative indexing starts at -1 down to -6. Negative indexing provides instant mathematical access to the end of a sequence. If you need the last character of a 1,000-word paragraph, index -1 isolates it immediately, without requiring the system to calculate the string's total length first. Every character in a string occupies an absolute position on this grid. This dual coordinate map provides the strict routing required for all data extraction algorithms. When we need to pull targeted subsets of data without violating the immutability axiom, we use an algorithmic tool called slicing. This blueprint displays the extraction syntax: start, stop, and step. The start boundary is inclusive, but the stop boundary is strictly exclusive. Passing the coordinates word 1 to 4 captures index 1, 2, and 3, which detach to form a new independent sequence, YTH. The step parameter determines the stride between extracted characters. Defaulting to 1 pulls sequentially. By deploying a negative step, like : -1, we force the system backward. This single command spawns a complete, newly allocated copy of the sequence in reverse order. Slicing never cuts or damages the original string. It strictly references existing spatial coordinates to clone specific characters into a fresh memory instance. Traversal is the systematic accessing and processing of each sequential character in a data structure, one by one. This split screen compares traversal methods. On the left, an older while loop tracks an integer, counting up from 0. Managing this integer introduces overhead. If index plus equals 1 is omitted, it creates an infinite loop or off by 1 error, crashing the program. The Pythonic for loop avoids this by interacting directly with the sequence objects. It automatically asks the string for its next character until the sequence ends. This native iteration eliminates the need for manual coordinate math. By removing the integer tracking entirely, we drastically reduce human error in the architecture. Beyond loops, Python provides an arsenal of built-in string methods. Because strings are immutable, these methods act as pure functional pipelines. They take in data and return new results without altering the source. These methods fall into 3 architectural roles: Boolean evaluators, returning true or false, extractors, locating targeted data, and transformers, generating formatted strings. This logical flowchart illustrates the critical difference between two extractor methods, find and index. When searching for a missing substring, find safely outputs a -1, allowing the program to continue. Index branches into a value error, a formal exception that instantly halts execution. A senior engineer deliberately chooses the fatal index method when missing data indicates a critical security flaw. If a mandatory security token isn't found, you want the system to halt immediately during validation. Transformer methods handle structural changes. The .split method is particularly aggressive in how it handles memory. By calling .split, you change the data architecture. The method scans the sequence, locates a specified separator, like a space or a comma, and divides the data, converting a single immutable string into a mutable list of smaller, separate strings. None of these powerful methods violate immutability. They process the rigid input sequence strictly to spawn entirely new logical evaluations or new data structures. To see these pipelines in action, consider a strict user registration system designed to defend against invalid database entries. The system enforces strict validation rules. The username must contain absolutely no spaces, consist strictly of alphanumeric characters, and possess a mandatory suffix, admin123user. Inside that string lies an invisible, system-breaking threat, a single trailing whitespace character, sitting at the very end of the sequence. Without a rigorous sequence of built-in string methods, this single invisible character will bypass basic human checks, fail the alphanumeric validation, and corrupt the database architecture. Watch this string pass through a pipeline node labeled .rstrip. It outputs a shorter memory block with the whitespace stripped away. We pass this clean string into .isalnum. With the space gone, it verifies only letters and numbers remain, outputting a true Boolean signal. Combining a cleaning method with an evaluator constructs an impenetrable shield against bad formatting. We execute final security by passing the clean block into the .endswith method, checking for user. It returns our second true signal. The suffix rule is met. By utilizing built-in methods, we sequentially chain complex logical verifications and filter data, all without ever risking mutation of the original raw input trace. The final system requirement states that validated data must be standardized into completely lowercase letters before permanent database storage. We execute the command username equals username.lower. In this diagram, you can see exactly what happens. The action does not change the capital A in place. The variable tag username physically detaches from the old mixed-case memory block and snaps onto a newly spawned all lowercase memory block. The old mixed-case memory block is left behind with no variable referencing it. Python's automated garbage collector, a background process that deletes unreferenced data to free up memory, will eventually locate and destroy it. Treating strings not as fluid text, but as immutable zero-index spatial arrays forces you to manage memory deliberately. This approach is the standard for writing secure, predictable, and professional Python architecture.